Today we're going to use that leading coefficient test as well as finding zeros to graph these polynomials by hand. So you'll notice in the book problems that they will say to use your graphing calculator just to check your answer. That's fine, you can do that, but the intent here is to essentially do everything on our own without the aid of the graphing calculator, and I'm going to show you through these two examples how we do that. All right, we will find the LCT first. We will find the zeros. Remember, those are the x-intercepts. And this is new for today. What we're going to do is we're going to see if any of those zeros have duplicates, or I should say have repeated values. So that's where the multiplicity comes in. And what you're looking at is the exponent right here on the factored form. They're using this little tiny k to represent that exponent. And so what you want to determine is if that power is an even or odd power. So that's what you're seeing here with the number 1 and the number 2 in that really tiny type. If that k, if that exponent is odd, then nothing really different happens. The graph will cross the x-axis at that number, at that x-intercept. However, if k is even, then the graph will touch the x-axis, but it does not cross the x-axis at that location. So you can kind of think of it as if the graph were going to bounce off and head back in the direction it came from, staying on the same side. So we'll see an example of that here in a moment. Then we need to find some more values in between those x-intercepts, and this final step will be to find the additional points. What we want to do is we want to find an additional point beyond and between. Here it just says between the zeros, but we want beyond and between, so on the left and far right side as well. Okay, here's our first problem. Number 1, we have this negative 1/4 times the x minus 2 quantity squared times the x plus 2 quantity squared. All right, so here is starting off with the leading coefficient test. We want to determine the degree as well as the leading coefficient. So we're looking at the largest exponent, and you might think the exponent is 2, but that's not the case because these are factors, and factors have to be multiplied together. So if you were to multiply these together, what would be the largest power then? It would be a 4. You'd have an x to the power of 4 if you multiplied all these together. So it's an actual degree 4, fourth degree polynomial. We want to know if it's odd or even. Of course it's even. That means both ends will go up together or down together. The leading coefficient is a negative 1/4, and so the negative sign is what we're looking at. And that means that we would expect the left side to fall and the right side to fall as well. So that's step 1. Step number 2, we want to find some zeros. So I'll work that right below the grid. So to find the zeros, we're going to set the output to 0 and work our way through this to solve for x. Now the first thing to do is recognize this is already in factored form, which is great. That means we can separate each factor and set each factor equal to 0, but I'm just going to restructure it here first before I do that. First of all, if we set this factor equal to 0, that's nonsense. Of course, negative 1/4 doesn't equal 0, so as a way of handling this, you can think of this as I'm going to multiply both sides by a negative 4, and that essentially just clears out the denominator, so you have 0 equals, and now that factor of negative 1/4 is gone. So you have an x minus 2 quantity squared. So think of that as x minus 2 times another x minus 2, and then you have the x plus 2 times another x plus 2. Separate each of those factors, setting each equal to 0, and we'll solve for each of them. So we will have answers of positive 2, negative 2, and negative 2. So obviously we have a multiplicity, right? So where you have the repeated values, that's where you have the multiplicity. So that's an even multiplicity. And if it is even, that means that we will see that bounce occur. Our graph will touch the x-axis, but it won't actually cross over at these locations. Now we still have to find some additional points to help us plot, but let's plot what we do have so far. Okay, so I've got my scale at 1 on both of these axes. Right now we have x equals positive 2 and x equals negative 2. We also know with the leading coefficient test that the left side is going to decrease, the right side is, I should say, the left side is falling, the right side is falling. So the graph is going to come up, and it won't actually cross over at -2. It's going to turn around, turn the corner, and kind of bounce right back down. So we want to know what's happening between these. So our rule of thumb is we want to find an additional point on the left side, on the far right side, and between each pair of zeros. So let's pick an input. Let's pick an x-coordinate that's somewhere here on the far left-hand side. So how about an input of -3? Where would that point be located? So we're going to evaluate the function with an input of -3. So just drop that in. So we have a -1/4 times that input of -3 with the -2 quantity squared be multiplied by input of -3 with a +2, that quantity squared. Now, even though we're not using our graphing calculators, we certainly can use our calculators to help us with these calculations, to find the output a little bit more quickly. So feel free to type that into your calculator just to help with the basic computation there. We'll have an output of -6.25. So we'll plot that point. And that makes sense because we know the left-hand side is falling. So yeah, there it'll be falling. Let's pick a point between. Let's pick one right in the middle. So how about at an input of 0? Setting up my input of 0. Here's showing my work. Again, that will give us a result of -4. So 0, -4. And then lastly, we want to point on the far right-hand side. So how about an input of +3? And I'm using my calculator here. We get the same result of -6.25 like we did before. That's because we have, it turns out it's an even function, right? That means it has symmetry about the y-axis. So now we bring it all together and graph a smooth curve through each of these, something like, well, I completely missed that one. There we go. Something like that. So there's the bounce, and there's the bounce. So we see that bounce occur whenever you have an even multiplicity of zeros. Let's see another example, and then we'll compare the two side by side. This is not in factored form, which means when we're solving for our zeros, we will have to factor it. But here's our terms listed in order of descending powers. Power of 3, power of 2, power of 1. So that's the first term you want to analyze to look at your leading coefficient test. We have a degree of 3. So for our purposes, we want to indicate that it's odd. And the leading coefficient is a +3. So that means the left side will fall and the right side will rise. Let's find our zeros. Setting the output to 0. And let's remove the greatest common factor. We can factor out an x, but we can do more than that. We can also factor out a coefficient of 3. So that leaves us on the inside the x squared minus the 5x plus 6. Always remove the largest possible factor that you can. That way the numbers that you have remaining are smaller and therefore easier to factor on the next step. It's a quadratic. We want factors that multiply to a -6 but have to add up to a -5. So that's factors of -3 and -2. Setting each of those factors equal to 0 and then solving each of them, we have zeros of 0, 3, and 2. So we don't have any multiplicity, we just have one value of each of the zeros, which means that when we graph this, there's no bounce effect. We will pass right through the x-axis. So we have one at 0, one at +2, one at +3. Again, we're falling on the left, we're rising on the right. We need to pick some additional points. So we want one on the far left, in between the first pair of zeros, in between the next pair of zeros, and one on the far right. So here we go. There's my list of additional points. Let's pick an input of -1. This is the one on the far left. So 3 times -1 cubed. minus 15 times the negative 1 squared, plus an 18 times the negative 1. Again, feel free to type that into your calculator just to help assist with the computation. How about an input of positive 1? That'll be between the first pair of zeros. That'll give us an output of 6. Let's do an input of 2.5. So that's between the middle and right 0. So we need something between 2 and 3, so I'm picking 2.5. And my output is negative 1.9, rounding to just the tenths due to the accuracy of our graph. And lastly, on the far right-hand side, let's evaluate the function with an input of 4. That will give us a point on the far right-hand side of our graph. Well, with some of these really large outputs, maybe we wanted to set the vertical scale to something other than 1, but no, that's okay. I've already marked it on my page. Let's just go with what we have. So that this first input of negative 1 with an output of negative 36, we're clear off the grid. So I'm just representing a dot here just to kind of say way down there. Next, 1, 6. Next, 2.5, comma, negative 1.9. And lastly, 4, 24. Again, we're off the grid, so I'm just putting a dot right up there at the top. So when we have these dots that are off the grid, that's okay, but we should just check to make sure that our computations match our expectation. We should be falling on the left and rising on the right, and we are. So there's our graph, something like that. We have one more example on the next page, and so I'm going to turn over and we'll finish up with that. We're not graphing here. In this case, what we're doing is we are going to take the given zeros with a certain multiplicity, and we're going to put them in factored form and multiply those factors back together again to find a polynomial function, the original polynomial function that has these qualities. So here's the list of factors. Remember, the factor is x minus the 0, and you drop the 0 in right there. So we have a 0 of 3, and with a multiplicity of 1, that means we just have an exponent of 1. Here we have a 0 of 2, so my factored form is x minus 2, and it's a multiplicity of 3, so it has an exponent of 3. 3 copies of those, in other words. So altogether, you have a total power of 4 that matches the degree 4. So what we're doing is multiplying these factors together. Now, there is a shortcut to multiplying that x minus 2 cubed. We've learned this in the past. I don't know if you remember it here. You could certainly use it. But let's say we don't remember it. Let's say we don't know what's going on. This is essentially the longer method, but it works. We have 3 copies of that same factor because of the multiplicity. So what we're going to do is I'll FOIL the first 2 together, I'll FOIL the second 2 binomials together, and then we'll keep on multiplying after that. So here we have x squared minus 5x plus 6, and here we have x squared minus 4x plus 4. What that means for us now is we have a lot of distribution. We'll take that x squared and we're going to distribute it to the 3 terms that follow. And I'll create a new column for each power of each descending power of x. So we have x to the 4th minus 4x, 4x cubed, and then we have a plus 4x squared. Then we'll take this negative 5x, we'll distribute that as well, and we'll start a new row down here, again matching the columns for each descending power. So I'm sort of dividing these up into the exponents that we see here. So negative 5x times the x squared, that's a negative 5x cubed, so I'll put that here in the column. What we're doing is we're just kind of grouping our like terms together to get them ready for combining in a moment. And then we're taking this positive 6, distributing it 3 times as well. So 6x squared, and then minus 24x, and lastly a constant term. So what we're doing is we're combining like terms, adding up each column. And then here you can just double check. Notice it was a 4th degree polynomial. We do have our largest power as a 4, so that matches as well. There's the polynomial function in general form.